Hi, everyone. Welcome to the Waymo Open Dataset session. My name is Zoe Yang, and I'm from Waymo Research. Today, my colleagues and I are here to share about the datasets that we have built and to announce the winners of the 2022 Waymo Open Dataset Challenges. It's really exciting to regather with the research community in person, and it's also great to see the audience on Zoom and YouTube. So thank you for being with us here today, and thanks to organizers for providing this platform. So to anyone who's new with Waymo Open Dataset, is one of the ongoing contributions that we're most proud of at Waymo. It's needless to say how important good autonomous driving datasets are to machine learning models and to the research community. And at Waymo, we have been working to contribute to the research community with one of the largest and most diverse autonomous driving datasets. We have a very talented team behind this effort. Here are the core engineering and research contributors who brings the open dataset to the community. And you hear from them shortly today. There are many more contributors from multiple teams at Waymo who are not on the slide, but made essential contributions. We first launched the open dataset in August 2019 with a focus on perception. In 2020 and 2021, we further expanded the dataset to enable tasks like motion forecasting and planning. We also conducted challenges on various topics with something new for each year. And now the open dataset has two datasets, perception dataset and motion dataset. The perception dataset has sensor data from LiDAR and cameras, and the motion dataset has over 570 hours of driving events. Both of these datasets are collected from Waymo vehicles in real life scenarios from multiple cities across different time of day. They're rich in diversity and interesting events, and equipped with high quality labels. And now we're in 2022, the third year of Waymo Open Dataset Challenges. This year, we further expanded the perception dataset to version 1.3 with a few sets of labels and a new set of segments. So in the perception dataset version 1.3 that we released this spring, we greatly expanded the features in the dataset. From the old labels as indicated in blue, which are 2D and 3D bounding boxes, to all the new features in yellow. This includes 2D and 3D human key points for 14 points from nose to ankle, as you can see on the picture. It also includes 3D semantic segmentation labels for 23 classes. You can see the picture on the bottom right. It includes association of 2D and 3D bounding boxes for pedestrians and cyclists, and 80 new scenes of camera data. So we're always working to expand the open dataset to contribute to more topics to the research community. And next, I'm really excited to introduce the newest addition to the open dataset, the camera video panoptic segmentation dataset. Our team just launched this last week, and it's available for download at our website, waymo.com/open. In this version 1.4.0 dataset, we provide panoptic segmentation labels consisting of the semantic class and instance ID for 1,000 images. This is split into 70,000 training labels consisting of 2,800 training sequences, where each one is 5 frames long. Similarly, we have 10,000 validation and 20,000 test labels. These are densely labeled to cover the whole run segments at 5 Hertz. In addition to the videos, we also label all 5 cameras to give a panoramic view of the scene. The dataset covers 28 semantic classes with instance ID for classes which overlaps with our bounding box annotations, namely vehicles, pedestrians, and cyclists. Finally, by leveraging our existing tracked bounding box annotations, we're able to provide consistent instance IDs between cameras and over time within each sequence that enables video instance segmentation in a number of extremely challenging scenes. And next up, I will pass it over to Vincent to talk about another Waymo dataset release that we just had last week.
Thank you, Zoe. Hi, everyone. I'm Vincent from the Waymo research team. So earlier this year, we published our BlockNerve work, which proposed a way to scale up neural rendering fields to reconstruct arbitrarily large environments. We showcase its capabilities in the Mission Bay district in San Francisco. Now, we newly released a data set that belongs to our work with 12,000 post multi-view images in San Francisco Mission Bay district, spanning over 1 kilometer. We hope that it will enable research into scalable reconstruction and view synthesis. And you can find it on the website today at waymo.com/research BlockNerve.
Thank you, Vincent, for sharing the BlockNerve dataset. Also last week, we launched the Waymo research website, where you can find the latest Waymo publications, including papers that will be presented at CVPR this year, like block nerve, and the Riddle LiDAR compression, and also papers that are related to open dataset, like the LET 3D AP metric that we used in this year's challenges. All right, without further ado, let's talk about the challenges. So this year we are holding 4 challenges with 2 on perception topics, which are 3D camera only detection and 3D semantic segmentation, and 2 behavior prediction challenges, which are motion prediction and occupancy and flow prediction. So in these challenges, we're introducing a few new task definitions and new metrics, which my colleagues will share with you shortly. The challenges run through March to May with prize money of 88,000. And shortly we'll review the winners of each challenge and hear from some of these teams. Although the challenges have ended, the leaderboards will remain open for future submissions. We hope our dataset and leaderboards will continue to serve the research community. So if you weren't a part of the challenges, we encourage you to check out the datasets and submit to the leaderboards. Over the 2-month challenge period, we have received impressive submissions from the global research community, both in terms of quantity and quality. From the quantity, we have received over 1,700 valid submissions from over 15 countries. We also engaged in over 400 discussions with the community on GitHub and through email. We're also very impressed by the high quality of the methods, with many pushing the state of the art in their respective fields. So the technical reports of the teams are now available online at the workshop website. We highly encourage you to check them out. They will also be coming soon to the Waymo website next week after the winner's announcement. On behalf of the Waymo Open Dataset team, I wanted to say thank you to everyone who submitted to this year's challenges. Thank you for your work to further advance research in autonomous driving. Next, let's take a closer look for each challenge. For each one, we'll first have the winner's announcement and then followed up by a spotlight presentation from one of the teams. Although some teams did not meet the eligibility criteria of the official challenge rules, so they could not be considered for prizes, but we still like to say thank you for all the great work you've done on Open Dataset. Now I will pass it over to my teammate, Wayne, who will introduce the 3D camera only detection challenge.
Thanks, Zoe. Hi, I'm Wayne from the Waymo research team. So this year we launched a new 3D camera only detection challenge. And the task is to given 1 or more images from the multiple cameras. We ask the user to produce a set of 3D upright bounding boxes of the visible objects in the scene. And we provide additional 80 multi-camera test segments for the evaluation. We also have the camera synchronized box for better training and evaluation targets. And we also propose a new dedicated metrics, which is called longitudinal error tolerant metrics. And the paper is available on archive. Feel free to check it out. And among the winning methods, we observe some trends, including the use of the bird's eye view feature maps with 3D detector heads on the camera features. And also how to use the camera features by lift and splat them into the 3D field with different methods. Now, without further ado, let me announce the winners of the 3D camera only detection challenge. For the 3rd place, we have CMKD, and the authors are Yu Hong, Han Dai, Xu Liu, Yong Ding, Andy Wang, Hongyang Zhang, Guangzi Chao, and they are from Zhejiang University, Muhammad bin Zayed University of Artificial Intelligence, and Pegasus Tech. Congratulations. And for the 2nd place, we have Focus 3D and VDAT 3D. And the authors are Tai Wang, Qin Lian, Chen Mingzhu, Xinge Zhu, Wenwei Zhang, and they are from the Chinese University of Hong Kong, the Hong Kong University of Science and Technology, and the Chinese University of Hong Kong Shenzhen, and Nanyang Technology University. Congratulations. And finally, we have the 1st place, which is Platformer Shanghai AI Lab. And the authors are Zixi Li, Han Mingdeng, Tianyu Li, Yang Yihuang, Chonghao Sima, Xiangwei Gen, Yu Gao, Wenhan Wang, Yang Li, Lewei Lu, and they are from Shanghai AI Lab and Nanjing University. Congratulations. And following, we will have the 1st place platformer to present their methods.
Hello everyone, I'm Zhiqi. It's my honor to be here to present our first place solution to the 3D camera-only detection challenge this year. These are our team members: 志奇、汉明、天宇、杨毅、崇浩、向威、于路、文海、李阳、乐伟. All of us are from Shanghai AI Lab. These are the outline of my talk today. Firstly, I will introduce our baseline method, BWaymo. BWaymo is one recently proposed camera-only 3D detection framework. It can achieve advanced performance by fusing multi-camera features and temporal information into BW features. In addition, the original framework of BWaymo is pretty clean and allows us to perform more improvements on top of it. Since BWaymo uses temporal information, first of all, we rearrange the sequence of Waymo dataset, makes the time interval of frames to be 0.5 seconds rather than the original 0.1 seconds. During training, we use 4 consecutive frames as a sample so that the current model can see the scenes from the past 1.5 seconds. Then the first improvement we did is that we used 2 additional modules to enhance the view features. We think the lack of optimization of view features in BWaymo is a potential bottleneck for the entire model. So after we opt multi-scale features from FPN, first we use corner pooling to refine it. We use top, bottom, left, and right corner pooling here. Then we use the view encoder with deformable attention to enhance the interaction of features at different scales. In our implementation, we use 3 encoder layers to balance the GPU memory consumption and the model capacity. Another bottleneck of BWaymo is that in the temporal self-attention, we predict offsets with linear function, which has limited receptive field to perceive the surrounding environment. So we use one convolutional layer with a control size 3 × 3 to predict the sampling offsets in the deformable attention here. To further leverage different detection frameworks for their potential in different scenarios, we use 3 different detection heads based on the BW features. One is the original deformable data head. We also use one anchor-free head center point and one anchor-based head free anchor. Our ultimate goal is to ensemble the results of different heads to achieve better results. Another key improvement we use is that we use LETLU-based AMS. The challenge of this year really is a new metric that is based on the LETLU, which gives more tolerance to the prediction results along the longitudinal localization. We found that this LETLU is friendly to the pedestrian category since the scales of pedestrian are too small to have intersection. With LETLU-based AMS, we can fill out many false positive results than other commonly used AMS methods. Beyond the above improvements, we also use many other commonly used tricks in the challenge. For example, we use EMA multi-scale training and multi-scale testing. We also use larger backbone and the BW scale to empower the model capacity. One additional 2D detector was used and jointly training with 3D detection head. We also use 2x export strategy and train more than 10 models and ensemble 26 model results. We use evolutional algorithm to automatically search the best ways of different model results. With these efforts, we get more than 20 points compared to our baseline. This figure shows the evaluation of our models. We can observe that our ensemble strategy can bring 4.8 improvement and LETLU AMS brings 2.9 improvement. Here is a demo of our final results on the test set.
Okay, thank you. Thank you very much.
Yeah, thanks for the presentation. So I'm Charles Qi from Waymo Research. Now I will introduce our next challenge, 3D semantic segmentation. So for this task, given one or more LiDAR range images and the associated camera images, we will produce a semantic class label for each LiDAR point. So compared to the previous 3D object detection task, this task required a more fine-grained understanding of the scene. To support this challenge, in Waymo Open Dataset, we added semantic labels of 23 classes to LiDAR points for a subset of the open dataset for around 32,000 frames or 4.7 billion points. So you can see a visualization of the labeled points in the figure below. Next, let's announce the winners for this challenge. For this one, we'll only announce the first 2 places. So the second place is the method Segnet3D-V2 from Jiale Li, Han Dai, Yong Ding from Zhejiang University and Mohammed bin Zayed University of Artificial Intelligence. Congratulations. And the first place is the method LiDAR Multinet from Dongqiang Ziye, Zixiang Zhou, Wei Jiachen, Yu Fei Xie, Yu Wang, Pan Qu Wang from Too Simple. Congratulations to the winners. And next, we'll have both teams present. And the method of second place, Segnet3D-V2 will be the first presenter.
Hello, everyone. I am Jiale Li, a member of the joint team Segnet3D from Zhejiang University and MBZU AI. Thanks to Waymo for inviting us to share a winning multimodal solution for 3D semantic segmentation challenge. Next, let's have a look at the overview of our method. There are 2 backbone branches for intramodal feature extraction. In the point cloud branch, we use a voxel-based 3D sparse unit to learn voxel features, and then obtain the point feature by devoxelization. In the bottom, we use HRNet to learn the image feature maps for the later intermodal feature fusion. Also, we decompose the multimodal data augmentation as the asymmetric transformations on the point cloud and the images. In addition to the self-contained method, the extension to multi-frame point cloud input and some other general tricks of test time augmentation and model assemble also benefit to the final submission. Go next. There are 2 steps to intermodal feature fusion. We first perform bilinear interpolation on the image feature maps based on the projected camera coordinates UV for feature association. We then fuse the associated features by concatenation and MLP. For our asymmetric multimodal data augmentation, the insight is to keep the order of the coordinate pairs C, UV, and XYZ among the points in synchronization. Bear this in mind, we can decouple multimodal data augmentation as 2 folds. We can apply arbitrary transformations to the point cloud and keep the images and the coordinates UV unchanged. We can even apply different transformations to the point cloud and the images if we ensure that the coordinates UV are synchronously transformed with the images. In such a manner, we can keep all the point cloud transformations and also introduce more image transformations, which diversifies the multimodal data augmentation and improve the model robustness. Next. This page reports our implementation details. Okay, go next. Next. The experiment results in table 1 validates that all the components contribute to the performance. Our method yields MILU 70.48 on the official leaderboard and can be retrieved by the submission entry of Segnet3D. Okay, next. More details can be found in our technical report. That's all our presentation. Thank you.
On to the first place method, LiDAR Multinet, please.
Hi, I'm Zixiang. In this presentation, I will introduce LiDAR multinet, the first place solution for the 3D semantic segmentation challenge. First, I'd like to introduce our amazing team members, Dongqiang, Ziwei, Jia, Yufei, and our team leader, Yu, and Sengpan Chu, and my advisor, Professor Furush, for the suggestion and support. This work is done during my internship at TuSimple. Previous space LiDAR detection and segmentation method tackled the problem with two separate network designs. On the contrary, our LiDAR multinet unifies those two tasks in a single network while achieving state-of-the-art performance on each task. Our novelties are threefold. First, we present an efficient LiDAR multitask network. Second, we propose a global context pooling module to extract global features. Third, we propose a second stage for the refinement of semantic segmentation, and it can be also used for accurate panoptic segmentation. As shown in this figure, our method can solve 3D semantic segmentation, object detection, and panoptic segmentation in a single network. Our network is designed based on the voxel-based 3D sparse encoder-decoder architecture. We implement the network using the open source SPComp library, whose author is currently working at TuSimple and released the new version of SPComp. Sparse convolution can significantly reduce the time and memory for the processing of 3D voxel features, but it limits the receptive field of the feature to the nearby valid voxels. Therefore, we propose a GCP module to enlarge the receptive field. The sparse 3D feature output by the encoder is first projected to a dense 2D BEV feature map, and then fed to a 2D multi-scale feature extractor. The resulting feature map is projected back to the 3D space, serving as the input of the decoder. The 2D branch of GCP can be also used for 3D detection. On one hand, we use it as an auxiliary task. More importantly, it transcended our method to a multitask network with only a small computational overhead for the 3D detection. To improve the consistency between the two tasks, we fuse the segmentation and detection results in a second stage. It takes voxel, point, and box level features to refine the segmentation scores in a point-based network. The result can be also used for panoptic segmentation. Completion study shows the improvement of each component in our method. Our proposed GCP module has the most significant contribution, increasing the MLU by almost 1%. Our method ranks the first place on the challenge leaderboard. It achieves the best performance in 15 out of 22 classes. In conclusion, we propose an efficient multitask network unifying major LiDAR perception tasks. As for future works, we will demonstrate the state-of-the-art result on more benchmarks and tasks. Thanks for listening. More information can be found in our report.
Thank you, and congratulations to the 3D semantic segmentation winners. I'm Scott from the Waymo research team, and I'll be presenting the results of the motion prediction challenge. First, we had a record number of submissions this year, so I'd like to thank everyone who participated. So what's new in the challenge this year is we added lane connections, lane neighbors, and lane boundaries to the data set. And we started to use the new soft MAP metric for the challenge ranking. As far as trends in the results, transformers performed very well on this task. Transformers or transformer-like methods took the two top places. Large ensembles we have seen in the results significantly improved the results. And to summarize for background, the task for a motion prediction challenge is to predict 8-second trajectories given 1-second agent history and map data for up to 8 agents. Now I'd like to present the results for this year's challenge. So we had an extremely close finish for third place with a razor-thin margin. So we've included the fourth place result as an honorable mention here. This is the method called MPA by Stephen Konyev, who was competing as an individual. So congratulations, Stephen. And in third place, we have the HBENS method by Jingyu Qian, Yifan Shuang, Juning Yang, Jiajie Chen, and Qiang Lu from Horizon Robotics. Congratulations to third place. And in second place, we have the golfer method by Xiaocheng Tang, Sohei Sadeghi Eshkevari, Haoyu Chen, Weidan Wu, Wei Chen, and Xiaoming Wang from DD Global. Congratulations to second place. And our winner in first place is the MTRA method by Xiaoshui Shi, Li Jiang, Dengxin Dai, and Bernd Schiele from Max Planck Institute for Informatics. Congratulations to our first place winner. All of these methods their technical reports are available on the website. I encourage everyone to read those to learn more about these methods. Now the MTRA authors will present their work.
Hello everyone. First, thanks for the invitation from the Waymo Open Dataset team. My name is Shaoshui Shi. I'm currently a postdoc researcher from MPI for Informatics, advised by Professor Bernd Schiele. Here I present our MTRA framework, the first place solution for the motion prediction check of Waymo Open Dataset Challenge at this year. Next, thanks. I will first introduce our motivation. For the motion prediction task in autonomous driving scenarios, existing approaches generally adopt two types of strategies to generate future trajectories. The first, goal-based methods utilize predefined goal candidates to localize the future destination of the agent, and then complete the trajectory waypoints for each selected goal candidate. And the second, direct regression methods directly regress multiple future trajectories from the same agent features by adopting a simple linear layer. Next. However, both of them have their limitations. The goal-based methods suffer from high computation and memory cost due to a large number of densely sampled goal candidates, while the direct regression methods generally converge slowly since various motion modes are regressed from the same agent feature. Next. To overcome these drawbacks and take the best of both methods, we propose the motion transformer framework, which adopts a transformer-based framework with a novel concept of motion query pair for motion prediction. Next, please. To be specific, we first adopt a simple transformer encoder network for context encoding, where both the agent history trajectory and the roadmap are represented as polylines. We adopt the PointNet-like polyline encoder for encoding the polyline features of agent history state and map polylines separately. And then several transformer encoder layers are adopted on the polyline nodes to learn the agent interactions and map topology for context encoding. Next, please. Then for the decoder network, we propose the novel concept of motion query pair for motion prediction, where each motion query pair contains a static intention query and a dynamic searching query. And these motion query pairs are considered as the learnable query positional embedding of transformer decoder layers to aggregate features from the encoder for predicting multimodal future trajectory. Next, please. Specifically, we first generate a small set of intention points for each category by adopting k-means clustering algorithm on the endpoints of ground truth trajectories. And each static intention query is a learnable positional embedding of a specific intention point, taking charge of predicting future trajectory of a specific motion mode, targeting at its corresponding intention point. Next, please. The dynamic searching query is also initialized as a learnable positional embedding of a specific intention point, but it will be dynamically updated in different decoder layer to extract trajectory-specific map features by collecting map features along each predicted trajectory, so as to provide more fine-grained trajectory features for motion refinement with stacked transformer decoder layers. Next, please. And finally, the queried feature of each motion query pair will be used to predict the Gaussian mixture model represented future trajectory for its corresponding motion mode. Next, please. And to further boost the performance, we also adopt a simple model ensemble strategy where we merge the predictions from several models and utilize non-maximum suppression to remove the redundant predictions, and the distance threshold of NMS is scaled along with the length of each predicted trajectory. And this simple model ensemble strategy facilitates taking the best predictions from multiple models. And here we can see that the model ensemble strategy achieves much better performance than the single model result. Next, please. Our approach finally ranks first on the test leaderboard of motion prediction check in this year's Waymo Open Dataset Challenge, outperforming other methods with remarkable margins. Next. Thanks for watching, and for more information of this work, please stay tuned on my homepage. Thank you.
Okay, thank you and congratulations, Max Planck Institute, on your winning entry. I'm Reza from the Waymo research team, and this is the last of the 4 challenges that we'll look at today. So the occupancy and flow challenge is defined as the same data set as the motion challenge, which we just looked at. A detection and tracking system gives us sparse agent states. And given that, we are asked to predict the bird's eye view occupancy and flow for both visible and occluded agents over the next 8 seconds. Before introducing the winning teams, let's look at some common trends we saw among the winning submissions. We saw 3 out of the 4 methods used transformer or attention blocks. 3 out of the 4 methods used focal loss to deal with the imbalance between occupied and unoccupied pixels. And we had the top 2 teams model larger field of views to see peripheral agents. And the top 2 teams are very close in score as well. And here are the winning teams. As honorable mention, we have Team Hope from Horizon Robotics, who got impressive results. Even though they were not eligible for the challenge prize, they are one of the 2 teams that will present their work today. And on this team, we had Yihan Hu, Wenxin Shao, Bo Jiang, Jiajie Chen, Shigi Chai, Jenny Yang, Jingyu Qian, Helong Zhou, and Xian Liu. In 3rd place, we have Vector Flow from MIT and Tsinghua University. And the authors are Xin Huang, Xiaoyu Tian, Zhangru Gu, Xia Sun, and Han Zhao. Congratulations to the 3rd place winner. In 2nd place, we have the method StrajNet from Nanyang Technological University, and the authors are Hao Chen Liu, Jiyu Huang, and Chen Liu. And lastly, the winner for our challenge in 1st place is Look Around by Dimitru Pavlovsky from Australia, who will give their presentation shortly.
Hello, my name is Dmitry Poplavsky. Today, I would like to present my solution to the Waymo Open Dataset Challenge. Well, the approach is quite simple. All the scene-related data is saved to the grid with separate channel for every feature of road structure, agents, and traffic lights. It projected to 64 channels and uses input to Ethernet-based segmentation model, directly predicting 8 steps of occupancy and flow. This approach works pretty well, but it certainly can be improved. The first obvious improvement is just to increase the input area so model could see more, and even project diff cars up to 8 seconds ahead. Another important improvement is to modify the loss function and select the right one. Like replacing log loss with focal loss has quite large impact on the final score. It also helped to use the combined occupancy and flow when occupancy is warp using the flow on every steps. And the final quite interesting improvement is to modify the model so it better describes the domain we're working with. And here I'm introducing the flow warp block. Well, it's always very useful to make sure that model can naturally describe the task. And CNN is quite useful here because it provides a translation variance, which is obviously applies, but it doesn't have the scale invariance, and it cannot easily very different position depending on your state. For example, if car is moving at 10 meters per second, for the next timestamps, you want to check different or previous position in space comparing when car is moving 20 meters per second. And to address this, I introduce such modification to Ethernet. So the implementation is quite straightforward. All Ethernet channels are combined together with FPN-like approach to generate flow and features. And then features are worked with this trainable flow to be projected back to Ethernet channels and added as residual connections. And this block is repeated 8 times, so model can query different points in space and use different features. Here's some visualization of the output flow and flow used by these internal blocks. And as expected, in many cases, the direction is quite similar. But in some cases, which is interesting, model decided to query the opposite direction to the flow of movement. And sometimes the offsets depends on the cars and different features. Oh, thank you.
Again on winning the challenge. And our last presentation for today is by Team Hope from Horizon Robotics. Please take it away.
Hello everyone, I'm Yihan Hu, and I'm here to present our work, HOPE, Hierarchical Spatial Temporal Network for Occupancy Flow Prediction. We're engineers from Horizon Robotics. Our method, Horizon OccuFlow Prediction, ranks first on the Occupancy and Flow Prediction Challenge leaderboard, and we are honorable mentioned as presenter in this challenge. Here's the outlines. First of all, let me introduce the overall structure. Our framework is composed of the input module, the encoder, the aggregator, and the decoder. As for the input, we adopted 2 different types of representations, the raster dense input and sparse 3D input. We first rasterize the dynamic information shown in orange and static information shown in blue on the broad view. And we aggregate the dense 2D representations by channel-wise concatenation. This 2D feature map is then used by a regular CNN encoder and transformer encoder. Also, by specifying the raster data, we adopted a 3D sparse representation where we separate the time and spatial domain. The 3D sparse features are then fed into a sparse spatial temporal 3D encoder. In our solution, we train 2 separate networks, one with CNN and transformer encoder, and the other one with CNN and sparse 3D encoder, and we ensemble the outputs as final results. Here are the details. For efficiency, we choose RecNet as our CNN encoder. Also, we choose Swing Transformer V2 for its local attention mechanisms. As another option, we choose sparse 3D encoder for its spatial temporal ability and efficiency. For aggregator, we choose BiPN to fuse smart-scale fine-grained features and enhance its features with sampled latent code. The latent variable is trained with conditional variation approach. We redesigned the latent variable structures in a meta-scale bird's-eye view manner. We designed the feature pyramid network with 3D convolutional bottlenecks. Dilated kernel and bottlenecks efficiently enlarge the receptive field, and 3D transposed convolution gradually unroll the temporal domain efficiently. Also, spatial upsampling is used to fuse smart-scale features. Then, a single icon rail TM layer is applied on top to generate and refine the final temporal features recursively. We use focal loss for both of the observed and occluded occupancy prediction, and use smooth L1 loss for flow prediction. Also, drift loss is applied to enforce the consistency between occupancy and flow prediction. We use scalar divergency loss to enforce the consistency of the predicted and observed future distribution. Then, we sum all losses as the final loss. We also used test time augmentation, stochastic weight average, model assembling, enlarged input, and half-precision training techniques. Here is the ablation study. Here is the leaderboard on test set. Here is our visualization on the validation set. Thanks everyone. Please refer to our technical report for more details.
Congratulations again to all the winning teams, and thank you for the fantastic work you have done on Waymo Open Dataset. Thank you everyone for joining us today. We look forward to Waymo Open Dataset contributing to more of your future work. And now I will turn it over to Henrik and the workshop organizers for the next session.